Welcome to G Fun Facts Online. Today, we're diving deep into one of the most critical challenges of our time, the quest for fresh water. As populations grow and climates change, the water we've always relied on is becoming less reliable. But humanity is fighting back, not just by managing what we have, but by engineering what we need. We're going to explore the cutting-edge technologies that are turning salty oceans, city wastewater, and even the air itself into pure, life-sustaining drinking water. Let's jump right in. Our first stop is the vast, untapped reservoir that covers more than 70% of our planet, the oceans. The technology that unlocks this resource is called desalination. For decades, the leading method has been a process called reverse osmosis, or RO. It's a beautifully simple concept that requires some seriously advanced engineering. In nature, water likes to move from a less salty area to a more salty area to balance things out. Reverse osmosis does the exact opposite. By applying immense pressure, often more than 60 times that of the atmosphere, we force seawater against a special membrane. This membrane is a high-tech filter, a sheet of polymer with pores so small that water molecules can squeeze through, but larger salt ions, minerals, and other impurities get left behind. The result is a stream of incredibly pure fresh water and a stream of highly concentrated salt water called brine. The heart of a modern desalination plant is its thousands of spiral wound membrane modules, all working together. But before the water even reaches them, it goes through extensive pre-treatment to filter out sand and solids that could damage the delicate membranes. The most energy-hungry part of the process is the high-pressure pumps. But a brilliant innovation called an energy recovery device, or ERD, has been a game-changer. The high-pressure brine leaving the system still contains a lot of energy. ERDs capture this energy and use it to help pressurize the incoming seawater, cutting the total energy demand by as much as 40%. The final step is post-treatment. The pure water from the RO process is almost too clean, lacking essential minerals. So minerals like calcium and magnesium are added back in to improve the taste and make it less corrosive to pipes. The water is then disinfected and sent to our taps. Of course, it's not a perfect solution. Disposing of the extra salty brine is a major environmental challenge, requiring sophisticated diffuser systems to protect marine life. And while it's become much more efficient, desalination is still energy-intensive, which is why there's a huge push to power new plants with renewable energy. To see what's possible, look at Israel's Sorek plant. It's one of the largest and most advanced RO facilities in the world. It produces over 600,000 cubic meters of fresh water every single day, supplying about 20% of the country's household water. Innovations at Sorek have pushed the cost of desalinated water to record lows. This plant helped transform Israel from a water-scarce nation into a water-surplus nation, proving the incredible potential of taming the oceans. From the ocean, let's turn our attention to a water source that's much closer to home, the water we've already used. For centuries, wastewater was something to be treated and discharged, a liability. But a new way of thinking is recasting it as our most reliable and sustainable water source. This is the world of water recycling. The most ambitious form of this is called potable reuse, which means turning wastewater back into drinking water. While the idea might sound unsettling, the so-called yuck factor, the technology to do it is incredibly safe and robust. The process uses a multi-barrier approach, where water passes through several redundant purification stages. After conventional primary and secondary treatment, which use screens and bacteria to remove solids and organic matter, the real magic begins. First, the water is pushed through microfiltration membranes, which act as a physical barrier to any remaining solids, bacteria, and even viruses. Next, it undergoes reverse osmosis, the same technology we just discussed in desalination. This removes the finest contaminants, like salts, heavy metals, pesticides, and pharmaceuticals. Finally, as a fail-safe, the water is zapped with a combination of powerful ultraviolet light and hydrogen peroxide. This is called an advanced oxidation process, and it destroys any trace organic compounds that might have slipped through the previous barriers. The result is water that is often purer than traditional sources. A prime example of this technology in action is the Groundwater Replenishment System, or GWRS, in Orange County, California. It's the world's largest project of its kind. The GWRS takes treated wastewater that would have been pumped into the ocean and purifies it through this three-step process. This ultra-pure water is then used to replenish the local groundwater aquifer, which supplies drinking water to 2.5 million people. The project has been a monumental success, demonstrating that large-scale water recycling is not just possible, but a safe and reliable solution. But for a true pioneer in direct potable reuse, we have to look to Windhoek, the capital of Namibia. Facing extreme aridity, Windhoek has been directly recycling its wastewater into drinking water since 1968. Their system proves that with the right technology and rigorous monitoring, this can be a safe, long-term strategy for water security. Overcoming the yuck factor is all about public trust, achieved through transparency, education, and rebranding the product as purified water, which is exactly what it is. Now, let's look up at the sky. In our concrete jungles, rain is often seen as a nuisance, causing floods and washing pollutants into our rivers. But a new approach called stormwater harvesting sees this rain not as a problem, but as a resource. The idea is to capture runoff from roofs, roads, and parking lots, treat it, and put it to use. At a small scale, this can be as simple as a rain barrel collecting water from a downspout for garden irrigation, or a rain garden, a landscape depression that allows water to soak into the ground, naturally filtering it and recharging local groundwater. But cities are thinking bigger. They are building large-scale systems to capture runoff from entire neighborhoods. One common method is to divert stormwater from drains into large infiltration basins. Here, the water slowly percolates through the soil, which acts as a natural filter, eventually replenishing the underground aquifers that store our groundwater. A global leader in this field is Melbourne, Australia. The city's Fitzroy Gardens stormwater harvesting system, for instance, captures runoff from a 67-hectare urban area. The water is treated, stored in an underground tank, and then cleaned by a biofilter garden before being used to irrigate the historic park, replacing 60% of the drinking water previously used for that purpose. The challenge with stormwater is that it can be contaminated with everything from heavy metals from cars to pesticides from lawns. The level of treatment depends on the end use, ranging from simple screens for irrigation to advanced multi-barrier systems if the goal is to create drinking water. By capturing stormwater, cities reduce flooding, improve the health of their rivers, and create a valuable new water supply, turning a liability into a major asset. So far, we've covered the big three: desalination, recycling, and stormwater. But engineers are also exploring even more audacious ideas. One is atmospheric water generation, or AWG. This technology literally pulls water out of thin air. The most common method works like a dehumidifier, drawing air in, chilling it over cold coils to condense the water vapor, and then collecting and purifying the resulting water. A more advanced method uses desiccants, special materials that are like sponges for water vapor. They can absorb moisture even at low humidity, and when heated, often by solar energy, they release the water as vapor, which is then condensed and collected. The biggest challenge for AWG is its high energy consumption, but new materials and designs are making it more efficient. While it's unlikely to supply a whole city, AWG is a fantastic decentralized solution for remote communities or disaster relief zones. And then there's the most sci-fi idea of all: iceberg harvesting. The concept is breathtakingly ambitious. Find a massive, stable iceberg calved from Antarctica, wrap it in a giant harness, and use a fleet of powerful tugboats, to slowly tow it thousands of kilometers to a water-scarce coast, like South Africa or Australia. There, it would be moored, and the pure, frozen fresh water would be melted and pumped ashore. The challenges are, of course, immense. The cost would be astronomical. A huge portion of the iceberg would melt during the long journey, and the risk of it breaking apart is high. There are also major environmental questions about the impact of introducing a massive block of ice and cold freshwater into a temperate marine ecosystem. For now, iceberg harvesting remains a tantalizing dream, but as technology improves, it's an idea that refuses to melt away. All of these technologies, desalination, recycling, stormwater harvesting, and even the more futuristic ideas, are part of a bigger shift in thinking. It's a move towards what experts call a circular water economy. The old, linear model was to extract water, use it once, and then discard it. The new, circular model is to reduce our consumption, reuse water as many times as possible, and even recover valuable resources like nutrients and energy from our wastewater. This circular economy is being supercharged by incredible innovations. Researchers are developing next-generation membranes inspired by biology that could drastically cut the energy needed for desalination. And artificial intelligence is being used to create smart water grids that can instantly detect leaks, predict demand, and optimize treatment processes in real time. The quest for freshwater is driving a revolution in engineering and a fundamental change in our relationship with water. By embracing innovation, investing in new infrastructure, and building public trust, we are moving from an era of scarcity to an era of sustainability, engineering a future where clean, reliable water is a reality for everyone. Thanks for listening to G Fun Facts Online.